Hello, this video includes information on intermolecular forces.
Chapter 10 deals with liquids and solids. Okay, so we are going to start with solids, liquids, and gases. And we have here a crystalline solid, and then we have the liquid state, and then we have the gaseous state. So when we talk about whether a substance is a solid or a liquid or a gas, there are essentially two things that affect the phase of matter. The first is what we call intermolecular forces. They're also called IMFs for short. And the intermolecular forces are the forces between molecules that are greatest in solids and the least in gases. And kinetic energy also helps to determine the phase of a substance. The higher the kinetic energy when we go from a solid to a liquid to a gas. So if we were to look at a solid has a definite shape and a definite volume. And that's because it has the greatest intermolecular forces and it has the lowest kinetic energies. Liquids are kind of in the middle. Gases have the least intermolecular forces, so there's less force holding the molecules together. And it has the highest kinetic energy, so the molecules are going to be moving around faster. So the physical properties of a solid or a liquid or a gas reflect the strengths of the attractive forces between the particles, which we call the intermolecular forces for those particles. So we're going to spend some time and talk about the different types of intermolecular forces. So before we talk about the different types of intermolecular forces, let's just kind of define what we mean by intermolecular forces. So what we have here, this is a hydrogen chloride molecule. And over here, we have another hydrogen chloride molecule. The intramolecular forces are the bonds that hold the atoms together in the molecule. Intra means within, like intramural sports are sports that are played between teams that are in the same school. Okay, so this bond here that holds the hydrogen to the chlorine is an intramolecular force. So ionic bonds or covalent bonds, which you learned in Chem 1, those are examples of intramolecular forces. The other type of force we're going to deal with is called intermolecular forces. And intermolecular forces are forces that hold molecules together in a liquid or a solid state. And intermolecular forces are much weaker than intramolecular forces. And the prefix inter means between, like intercontinental flights are ones that go from one continent to another continent. So going from the United States to Europe is an example of an intercontinental flight. This force here is called an intermolecular force because it's between two molecules. Now, you've already talked about the intramolecular forces in Chem 1. We're going to deal with the intermolecular forces here in Chem 2, and they're related. So there are several different types of intermolecular force. The weakest type of intermolecular force are called London forces, or sometimes they're called London dispersion forces. And they're very weak, attractive forces that result between instantaneous dipoles and induced dipoles that are caused by uneven distribution of electrons in atoms or molecules. So let's look at two examples of London forces. So let's say that we have this helium atom here and this second helium atom here. So this is A and this is B. And if the electrons are evenly distributed in these two atoms, we have no polarization. We have no positive or negative end to this atom here or this atom here. But electrons are always moving around at very high rates of speed outside the nucleus of an atom. And they're not always evenly distributed in that atom. Sometimes the electrons might be collected on one side of the atom. And that would cause that side of the atom to have a partial negative charge. That's what this symbol here means. And since the electrons are kind of congregated on this side of the atom, that's going to make this side of the atom partially positive. So what we have is what's called an instantaneous dipole in atom A. We've got a negative end and we've got a positive end in this atom. And it's instantaneous because it's just going to be there for an instant in time, and it has to do with the fact that the electrons aren't evenly distributed in this atom. Well, what this instantaneous dipole will do is it will induce a dipole in neighboring atoms. So if this atom has a partially negative side here and a partially positive side here, this partially positive side will attract the electrons in this B atom. The electrons are going to get pulled kind of over more towards this side. And now we've induced a dipole here. Well, unlike charges attract each other. So the partial positive here will be attracted to the partial negative here. And that's what we mean when we talk about a London force. Now, we can look about those London forces in molecules as well. It's the same concept. So here we have the diatomic molecule of hydrogen, and we'll just say that's A. And here we have the diatomic molecule of hydrogen, and we'll say that's B. And if the electrons are evenly distributed in this molecule and evenly distributed in this molecule, there's no polarization. But the electrons are moving around at really high rates of speed, and there could be an instant where the electrons are kind of all congregated over here, which would give us a partial negative side and a partial positive side to our molecule. We have an instantaneous dipole in molecule A. What that will do is it will cause or induce a dipole in molecule B, because the positive side of this molecule will attract the electrons in this molecule. And the partially positive end of this molecule will be attracted to the partially negative side of this molecule. And that's a London force. It's a force of attraction, an intermolecular force that will hold these two molecules together. And London dispersion forces are very weak intermolecular forces. They're caused by an instantaneous dipole and induced dipoles that are produced by uneven distribution of electrons in atoms or molecules. So if we were to look at fluorine, chlorine, bromine, and iodine, they're all diatomic molecules. They're all nonpolar, but they have the ability to form instantaneous dipoles. Now, if we were to look, their melting points and their boiling points and their states of matter are all dependent on the strength of the intermolecular forces. So as we go from chlorine or from fluorine to chlorine to bromine to iodine, the molecules are getting bigger. The number of electrons in the molecules are increasing. So the chance that we're going to have an uneven distribution of electrons in iodine is much greater than in fluorine. So we're going to see more easily instantaneous dipoles being formed in iodine than we are in fluorine. So the London forces in iodine will be stronger than the London forces in fluorine. So what does that mean? Well, if the London forces in fluorine are weaker, it's easier to change them from a solid to a liquid or melt them, or change them from a liquid to a gas or boil them. And fluorine is a gas at STP, or standard temperature and pressure. If we were to look at bromine, because it's more likely to have an instantaneous dipole, it will have stronger London forces, which means that its melting point will be higher than fluorine. Its boiling point will be higher than fluorine. And bromine is actually a liquid at standard conditions, at STP. It's actually only one of two liquids on the periodic table, bromine and mercury. Now, iodine is more polarizable. It's the most out of these four, which means the London forces are the strongest in iodine. So iodine has the highest melting point. It has the highest boiling point. And in fact, it's a solid at standard conditions. So the strength of the intermolecular forces help us with the physical properties of the substance. It'll help us with the melting points. It'll help us with the boiling points. And it'll also help us with identifying what state of matter that substance would be in. How are London dispersion forces, LDF, or just London forces for short, and shapes related? So let's say we were to look at pentane. Okay, pentane has this Lewis structure. And we wanted to compare it to isopentane, which has this Lewis structure. Now notice that they're both C5H12. The difference is the way the atoms are arranged. And then if we were to look at neopentane, it's also C5H12. These are all isomers of each other because they have the same chemical formula. But neopentane is a much more compact molecule. So how does the shape of the molecule affect their characteristics? So over here on the right, this is pentane. Okay, it's got the largest contact area, which means it would have the strongest London dispersion forces. If we were to look at isopentane, it looks a little bit like this. So we have a little less surface area. So there's a little less attraction. And if we were to look at neopentane, it's much more compact. So it's got much less surface area. It has the weakest London dispersion forces. Now, look at the boiling points. They're related to the strength of the intermolecular forces. Since pentane has the largest surface area and the most London dispersion forces, it has the highest boiling point. If we were to look at neopentane, because it's a much more compact molecule, it has a smaller surface area. The London forces are much weaker here, so it's easier to change it from a liquid to a gas. It has the lowest boiling point. So we can look at the structure of molecules and rank them with their physical properties. Now, you can't say for sure that the boiling point of pentane is 36 degrees Celsius. We can't figure that out. from their intermolecular forces, but we can tell that a pentane will have a higher boiling point than neopentane. So we'll be able to kind of rank things based on the strengths of their intermolecular forces. The strength of the intermolecular forces increases with the contact area between the molecules. So the more contact area there is, the stronger the intermolecular force is going to be. So the next type of intermolecular force, so we've gone through London forces. Now we're going to go through what are called dipole forces. So these are a little bit stronger intermolecular forces than London dispersion forces. And they form between molecules that have dipoles, not instantaneous dipoles like we saw in London forces, but they have permanent dipoles. So if we have a molecule here that has a positive end and a negative end because of the difference in the electronegativity, and we have another molecule here that also has a dipole, a negative side here and a positive side here, unlike charges attract each other. So we would have an attraction between the positive side of this molecule and the negative side of this molecule, and the negative side with the positive side. Now, we would have an attractive force here. The negative side of this molecule would be attracted to the positive side of this molecule. This wouldn't happen, okay, because like charges repel each other. Molecules aren't going to arrange themselves like this. And the same here, molecules aren't going to arrange themselves like this because like charges repel each other. And again, the difference between dipole forces and London forces is London forces are caused by instantaneous dipoles, whereas dipole forces, these are constant dipoles in a molecule. So dipole force is an attractive intermolecular force resulting from the tendency of polar molecules to align themselves positive to negative, unlike charges attract each other. Now, that can be in all different directions. So if we have a molecule here, it's going to arrange itself so that we maximize the attractive force here, we minimize the attractive force here, or the repulsive force here. We maximize the attractive force, we minimize the repulsive force. That's dipole intermolecular forces. Now, if we have three molecules here that all have about the same molar mass, their London dispersion forces are similar. But C3H6 is a non-polar molecule. It doesn't have a dipole moment. It doesn't have any polarity to it. Whereas CH3CN is very polar. Because we're increasing the polarity, we're increasing the strength of the intermolecular forces, which in turn is increasing the boiling point. Because in order for us to change something from a liquid to a gas, in order for us to boil something, we have to break those intermolecular forces. The stronger the intermolecular forces, the more energy is required and the higher the boiling point. The weaker the intermolecular forces, the less energy to change the substance from a liquid to a gas, and the lower the boiling point. So again, intermolecular forces are going to be related to those physical properties of substances. Now, it's important to know that every molecule, every substance has London dispersion forces present. Sometimes the London dispersion forces are the only type of forces that are present. But oftentimes we're going to have other types of intermolecular forces as well. And the London dispersion forces then are much less significant. So if we were to look at dipole intermolecular forces, those are going to supersede the London dispersion forces, which are also present. The third type of intermolecular force, so again, we're talking about intermolecular forces. We dealt with London forces. We dealt with dipole-dipole forces. The third type is called hydrogen bonding. And it's not quite a bond. We'll talk about that in a second. But when we talk about hydrogen bonding, it is a type of intermolecular force that forms between molecules if within the molecules, the intramolecular forces, we're looking at hydrogen bonded to either nitrogen, oxygen, or fluorine. Now, nitrogen, oxygen, and fluorine are very highly electronegative elements, meaning that they have a high pull for electrons in a bond. So what the nitrogen and the oxygen and the fluorine would do is they would pull the electron away from the hydrogen. And that's going to expose the positive nucleus of that hydrogen atom. And what that positive hydrogen atom will do then is it will be attracted to lone pairs of electrons on adjacent molecules. And it's this attraction here that gives us what we call hydrogen bonding. And again, even though we call it hydrogen bonding, HB for short, it's not really a bond. It's not an intramolecular force. It's an intermolecular force that's formed because within the molecule, hydrogen is bonded to either nitrogen, oxygen, or fluorine. Now, hydrogen bonding is the strongest of the three intermolecular forces. So let's look at what that does. So if we were to look at this molecule here, okay, it's called nitrile fluoride. It doesn't matter what it's called necessarily, but it is a polar molecule. It does have dipole-dipole intermolecular attractions between this molecule and the next molecule. And that's a fairly strong intermolecular force. But if we were to look at water, okay, water, here's one water molecule. We've got oxygen bonded to hydrogen within the molecule. This is an intramolecular force, okay? It's a polar covalent bond within the molecule. And oxygen, because it's so much more electronegative than hydrogen, the oxygen is going to pull the electrons closer to itself. So oxygen is going to be partially negative and the hydrogens are going to be partially positive. That partially positive hydrogen here is going to be very attracted to the oxygen in the next water molecule. That's a hydrogen bond. Because hydrogen bonding is so much stronger than dipole-dipole intermolecular attractions. This FNO is a gas at room temperature, whereas water is a liquid at room temperature. So let's look a little bit more at hydrogen bonding. Okay, first over here, I just put the electronegativity values for hydrogen, fluorine, oxygen, and nitrogen. And just as a quick review from Chem 1, electronegativity is a value that gives us the relative pull that an atom has for electrons in a bond. And if we look, fluorine, oxygen, and nitrogen are very highly electronegative, much more so than hydrogen is. So fluorine, oxygen, and nitrogen are going to pull the electron from the hydrogen more towards themselves. So what does that do? Okay, well, that's going to give us this intermolecular force that we call hydrogen bonding. So let's look at this picture here. This is a water molecule. Okay, H2O is right here. Okay, this line here is an intramolecular intermolecular force. This is a covalent bond. This is also a covalent bond. And that's what's holding the two hydrogens to the oxygen in this water molecule. Okay. Now, here's another water molecule. Okay. H2O. This is an intramolecular bond. This is an intramolecular bond, and that's what's holding this water molecule together. And the same thing for this water molecule here, and this water molecule here, and this one here. Now, because oxygen is so much more electronegative than hydrogen is, the electrons get pulled closer to the oxygen. So the oxygen has a partial negative charge, whereas these hydrogens have partial positive charges. Well, that's going to influence the water molecule next to it, because since this hydrogen is partially positive, it's going to be attracted to the lone pairs of electrons on this oxygen. That's what holds this water molecule to this water molecule. So this dotted line is a hydrogen bond. It's an intermolecular force that holds this water molecule to this water molecule. Now, the same thing happens here, okay? This oxygen has lone pairs of electrons on it. This hydrogen is partially positive. There's an attraction between this positive hydrogen and this negative oxygen. This is a hydrogen bond, an intermolecular force that holds this water molecule to this water molecule. Now, if this hydrogen bond here is super strong, we're going to be looking at water in the solid state. But if this is a little bit weaker, we'd be looking at water in the liquid state. And if this were almost negligible, we'd be looking at water in the gaseous state. Again, when we look at hydrogen bonding, okay, HB, hydrogen bonding, it's an intermolecular force, okay? It's actually just a really strong dipole-dipole attraction. And it holds molecules together in the liquid or the solid state. Now, the molecules still have dipole-dipole and London dispersion forces, but they're much weaker than the hydrogen bonding. So the hydrogen bonding would be the dominant intermolecular force when we look at water molecules in a sample. So let's look at a couple other examples of hydrogen bonding, just to make sure we understand what we're doing before we look at some properties. So here, this is an NH3 molecule. It's ammonia. Okay, and if we look at this ammonia molecule, we have nitrogen bonded to hydrogen and hydrogen and hydrogen. This solid line is an intramolecular force. It's a polar covalent bond that's holding the hydrogens to the nitrogen. This is another ammonia molecule where we've got the three polar covalent bonds, which are intramolecular, holding this molecule together. Now, because this is a very polar bond, the electrons from hydrogen are getting pulled towards the nitrogen. Hydrogen is partially positive. The nitrogen is negative. So the attraction between this ammonia molecule and this ammonia molecule is this dotted line here. This is an intermolecular force known as a hydrogen bond. Now, we can look at it in HF molecules. Okay, so we've got an HF molecule here where fluorine is much more electronegative, so partially negative, partially positive. This is a second hydrogen fluoride, okay, partially positive, partially negative. Now, the partially positive hydrogen will be attracted to the partially negative fluorine by this hydrogen bonding, this intermolecular force that holds this molecule to this molecule. And the same thing here. The partially negative fluorine will be attracted to the partial positive hydrogen by a hydrogen bond, which is an intermolecular force holding this molecule to this molecule. And then we can look again at water, okay, where we've got our water molecules. This is a hydrogen bond. This is a hydrogen bond. All these dotted lines are hydrogen bonds, which are a type of intermolecular force, the strongest of the types of intermolecular forces that will hold molecules together in a solid or a liquid state. So if we were to look, here's water, water. So these are all water molecules. The little dots are our intermolecular hydrogen bonds. And what that actually does is it helps to explain why ice has a lower density than liquid water. So if we put an ice cube into water, it floats, okay? And that's very unusual. Most substances, when they go from a liquid to a solid, they become more dense, and things that are more dense sink. Okay, water is different. When water forms these hydrogen bonds between the water molecules, it actually gives us a very regular arrangement of water molecules, which increases the volume of the water. So as water goes from a liquid to a solid, it increases its volume. Okay, that's why water expands when you freeze it. Okay, and since the volume increases, the density decreases and ice floats in water. So if you've ever taken a soda can and put it into the freezer to get it cold really fast and then forgot about it, and then you go back the next day, that can will have exploded, because as the water goes from a liquid to a solid, it expands. Its volume increases and the can bursts. All right, so now let's start connecting the intermolecular forces to some physical properties. And there are trends. So let's look at boiling point as our trend. Okay, so the blue line here, we're looking at elements that are in group 16. So we've got sulfur and selenium and tellurium. Okay, and if we look, as we go down the group, we're increasing the intermolecular forces, so the boiling point goes up. Okay, we see the same thing when we look at HCl and HBr and HI. Okay, as we go down a group, the strength of the intermolecular forces increases and the boiling point increases. So what we would expect, if we're looking here, this is at the bottom of the group. Okay, as we go up the group, the strength of the intermolecular forces goes down and the boiling point goes down. So we would expect this trend to continue when we get to this top of each of those groups. What actually happens is this. Okay, if we were to look at group 16, okay, as we go up the group, okay, the strength of the intermolecular force goes down and the boiling point decreases until we get to the top of the group. Okay, when we get to H2O, it's got a much higher boiling point than any of the other elements in that group or that column. Okay, the same thing when we look at column 15. As we go up the group, the intermolecular force decreases. So the boiling point goes down, but then when we look at the top of the group, it goes way up. The reason for that is when we look at H2O, or we look at HF, or we look at NH3, these all have hydrogen bonding, which are much stronger intermolecular forces than dipole-dipole intermolecular attractions we have here. Now, where else can we see hydrogen bonding? Just to kind of throw in maybe biology, because we do have a lot of people who are biology majors or pre-med majors or something along those lines. Okay, so you've probably heard of and done some work with DNA. And when you look at DNA, DNA is a double helix, okay, made up of nucleotides that are linked together by hydrogen bonding. So when a DNA molecule unzips itself so that it can go through the process of replication or transcription, it's the hydrogen bonds between the bases that break to unzip the molecule. And then those hydrogen bonds reform when the molecule zips back up. So when thymine is bonded to adenine, it's bonded by hydrogen bonding. Or when guanine is bonded to cytosine, it's held together by hydrogen bonding. So when DNA unzips itself, it's the hydrogen bonds that we're breaking. And then when it zips itself back up, it's the hydrogen bonds that are reforming between those nitrogenous bases. All right, so let's do some practice, okay? So what we have to do is we have to decide what type of intermolecular force is holding these molecules together. And then we're going to be arranging them by increasing boiling point. All right, so what we have to think of first, we have to draw our Lewis structures, and then decide whether or not we have a non-polar molecule, which means we have very weak London dispersion forces, which means they're going to have low boiling points. Or do we have dipole intermolecular forces, which are a little bit stronger and would have higher boiling points? Or do we have hydrogen bonding, which would be the strongest type of intermolecular force, and then it would have the highest boiling point? So let's look at A. Okay, we have HCl, we have H2O, and we have SiH4, silicon tetrahydride. Okay, so HCl is a polar molecule. Okay, so we're not going to be looking at London forces. We're either going to be looking at dipole intermolecular forces or hydrogen bonding. Now, here's the misconception. A lot of people think that because there's hydrogen in this molecule, it has hydrogen bonding. That's not always true. In order for us to have hydrogen bonding, hydrogen has to be bonded to fluorine, oxygen, or nitrogen, very electronegative elements. Chlorine is not one of those. So we will have dipole intermolecular attractions between this HCl molecule and the one next to it. Now, H2O, we've looked at that a couple of times, so we should already recognize what type of intermolecular force it has. But H2O has hydrogen bonded to oxygen within its molecule. So it's going to have hydrogen bonding between molecules. And hydrogen bonding is stronger than dipole intermolecular attractions. Silicon tetrahydride. We might have to draw that out using our Lewis structures. But if we were to think about it, we've got silicon in the center, and we have 4 hydrogens around that silicon. So this is a tetrahedral shape, and it's non-polar. So since it's non-polar, even though it's got hydrogen in it, okay, it's evenly distributed, it's a non-polar molecule, we're going to have London dispersion forces holding these molecules together. So we've got London forces here. We've got hydrogen bonding here. And we've got dipole-dipole intermolecular attractions here. That's the first thing we need to do. Then we need to order them. The stronger the intermolecular force, the more energy is required to boil it, the higher the boiling point will be. The weaker the intermolecular force is, the lower the boiling point will be. So London forces are weaker than dipole-dipole forces, which are weaker than hydrogen bonding. So our order would be silicon tetrahydride, we would expect to have the lowest boiling point because it has the weakest intermolecular attractions. Hydrogen chloride, we would expect to be in the middle because it's got dipole-dipole. Water, because it's got hydrogen bonding between its water molecules, would have the strongest intermolecular forces, so the highest boiling point. So let's think about the next example. We've got fluorine, chlorine, bromine. Okay, these are all non-polar molecules. The only type of intermolecular force we can have between non-polar molecules is London forces. They all have London forces. But the strength of the London forces is determined by the polarizability of the atoms. The more electrons they have, the more polarizable they are, the more likely they are to have instantaneous dipoles, and the stronger the London forces will be. Well, fluorine's at the top of the halogen group. Chlorine's a little bit farther down and bromine's a little bit farther down. So that means fluorine is the smallest, has the least electrons, followed by chlorine, followed by bromine. So fluorine would have the lowest boiling point. Bromine would have the highest boiling point. Now, they all have fairly low boiling points, but we can rank them from fluorine to chlorine to bromine because of their polarizability. Now, C, CH4, C2H6, C3H8. These are all non-polar molecules. The only type of intermolecular force we can have in non-polar molecules is London dispersion forces. So it's kind of like question B. So we need to decide which one of these molecules is more polarizable. Well, the bigger one with the more electrons is going to be more polarizable. So that means this is the least polarizable. So we'll have the weakest London forces. CH or C3H8 will be the most polarizable. So it'll have the strongest London dispersion forces. The stronger the intermolecular force, the higher the boiling point. So if we wanted to rank these, they're actually in the right order. We would expect CH4 with the weakest intermolecular force to have the lowest boiling point. And we would expect C3H8, which has the strongest London forces, to have the highest boiling point. D, oxygen is non-polar. Okay, two oxygen atoms bonded together. Nitrogen is non-polar, two nitrogen atoms bonded together. NO, nitrogen monoxide, is polar. Okay, it's two atoms of different elements bonded together, where oxygen is a little bit more electronegative than nitrogen. So we're going to have dipole-dipole intermolecular attractions in NO. We're going to have London forces in O2 and N2. So that means that NO is going to have the highest boiling point. Then we need to think about oxygen and nitrogen. Oxygen has more electrons in it than nitrogen does. That means oxygen is more polarizable, which means it will have stronger London dispersion forces. Nitrogen has less electrons, it's less polarizable, it will have weaker London forces, so it'll have a lower boiling point. So that's the thought process we need to go through. So when we rank them, although nitrogen and oxygen both have London forces, which are super weak, nitrogen will be weaker because it has less electrons. Nitrogen monoxide will have the strongest intermolecular forces because it's a polar molecule. So we can take the types of intermolecular forces to help rank substances according to their physical properties. And we need to be able to kind of visualize and draw the Lewis structures and know the molecular geometries in order to determine the intermolecular forces. So it's all related back to Chem 1 and those Lewis structures that you went through. Now these are drawn out for you, might make it a little bit easier to do. So we've got 4 Lewis structures drawn for us. Take a look at each of them and rank them from 1 to 4, 1 having the lowest boiling point and 4 having the highest boiling point. Here we have a non-polar molecule, and here we have a non-polar molecule. So 1 and 2 will have the weakest intermolecular forces. They'll have London dispersion forces or London forces. So now if we look at them, this is a smaller molecule. It'll have the weakest London dispersion forces, so it'll have the lowest boiling point. Okay, that means that this one here will be 2. Now, if we look at these molecules here, okay, we've got within the molecule, we've got oxygen bonded to hydrogen. Okay, so that means this hydrogen is partially positive and this oxygen is partially negative. Okay, we've got the same thing over here. Okay, because oxygen's more electronegative, the electron from hydrogen is going to get pulled closer to the oxygen. We've got a partially positive and a partially negative end here. We're going to have hydrogen bonding between this molecule and the next molecule. Okay, well, the same thing's here. Okay, we've got hydrogen bonded to oxygen. We're going to have hydrogen bonding here. But here we only have one place where we're going to be seeing that hydrogen bonding, whereas here we've got 2 places. So the hydrogen bonding in this third molecule will be stronger than the hydrogen bonding here. So this will have the third highest boiling point, and this one will have the highest. So 2, 1, 4, 3. So let's look at one more. Okay, we've got 3 molecules here. We want to arrange them by increasing boiling point. So really, we're arranging them by increasing intermolecular forces. Okay, which one's got the weakest? Which one's got the strongest? So this first molecule is non-polar. Okay, it doesn't have a positive end and a negative end. It's pretty symmetrical. So this has London forces. Those are pretty weak intermolecular forces. This one has oxygen bonded to hydrogen here. So we're looking at hydrogen bonding, holding molecules of this type together. That's much stronger. And then here, this is also a non-polar molecule. This is going to have London dispersion forces. So the second one here has to have the strongest intermolecular forces and the highest boiling point. If we look at this one and this one, They're both non-polar, but this one here is much more compact. We have less surface area, which means we have weaker London forces, which means we're going to have a lower boiling point. So this would be the lowest. This would be 1. This would be 2. This would be 3.